Okay, in this video I'm going to continue talking about growth curve modeling using SPSS. This is the final set of examples coming from this book right here in Chapter 5. The book is Multi-Level and Longitudinal Modeling with IBM SPSS, and the chapter is on examining individual change with repeated measures data. So the data set, which I downloaded from this website, looks like this, and essentially it's reflects an experimental design where we had a group of students who were randomly assigned to either a treatment or a control condition. And we were essentially looking at change over time in terms of their math scores. So basically math scores were measured at 4 time points. So the repeated measurement at level 1 is the math variable. So this would be student 1 measured at times 1, 2, 3, and 4 in terms of math scores. So the data set incorporates a level 2 identifier, which is identifying the students. Math is the level 1 outcome variable and reflects the repeated measurements in terms of math score. The time variable is this variable right here, and it's coded 0, 1, 2, 3, 0 through 3, reflecting essentially the initial time measurement, time 2, time 3, and time 4. The coding on it with 0 basically is utilized to help us to better interpret the intercepts of the students' growth trajectories as well as the grand mean of those intercepts. As a bit of a refresher, when we're looking at growth curves, keep in mind that we're looking at change over time on some variable. And so when we're looking at, in this case, we'll have student level data. We have measurements at time 1, 2, 3, and 4. And the coding of the time variable basically allows us to interpret the measurement at time 1 as reflecting the student's initial status in terms of their math scores. So we would expect perhaps there to be variation in their initial status in terms of math scores, and then also potentially variation in terms of the slopes. So that's essentially why the time variable is coded the way that it is. So again, we have ID as a level 2 identifier. We have math as being our level 1 outcome variable measured at 4 different time points, coded 0 through 3. And then a treatment variable reflecting a code of 0 reflects a student that was assigned to the control condition, and a code of 1 reflecting a student that was assigned to a treatment condition. So to carry out our analysis and following along with the example provided in the text, we're going to go to Analyze, Mixed Models, Linear. We'll move the ID variable over to the subjects box, and we'll move our time identifier, if you will, over to the repeated box. The default in SPSS is a repeated covariance type that is a diagonal matrix. In other words, it assumes unequal variances in the residuals at each of across the 4 time points, but it assumes no correlated residuals between time points. So that's what the diagonal covariance type is essentially implying. Obviously, there are other options that are available to you, but this is the one that is provided in the current demonstration. So we'll click on Continue and move Math over to the Dependent Variable box. We'll move Time and Treatment over to the Covariance box. Next we'll click on Fixed and move Time and Treatment over. Really in the presentation in their book, in their chapter, they went ahead and actually incorporated the time by treatment interaction, but we'll start off this demonstration with just looking at the effects of time and treatment, and then we'll add in the cross-level interaction. So under random, we'll move ID over from the subjects box to the combinations box, click on Include Intercept, and then we'll move time over here as well. So in other words, what we're basically going to be doing is estimating the variance in the students' intercepts from their growth trajectories, as well as the variance in their slopes. So now if we left it under variance components for the covariance type, then we would just be estimating the variances for the intercepts and the slopes. But keeping consistent with their presentation, we'll go ahead and select unstructured, meaning that we're going to be estimating both the variances of the students' intercepts and slopes, as well as the covariance between the two. Okay, so keep in mind too that in this particular demonstration, we are essentially treating the growth in terms of students' math scores as following a linear trajectory. So the fact that we're incrementing time by 1 unit, we're essentially modeling linear growth trajectories. But again, because we've clicked under random and included time as randomly varying component of those growth trajectories, we're essentially allowing there to be variation in terms of the slopes over time. So in other words, the students can exhibit variation in those linear trajectories. Okay, so under estimation, we'll leave this as restricted maximum likelihood. And under statistics, we'll go ahead and click under parameter estimates, tests of covariance parameters, and covariances and random effects. When we click on OK, you'll see that in our model dimension table, we get a layout of our model parameters and so forth. You'll notice that we're going to have a fixed effect for the intercept, which is essentially going to be the grand mean of the student's initial status on their math scores. We'll have a fixed effect for time, which is the grand mean of the slopes for the time time across students. And then we'll also have a fixed effect for treatment, which is essentially going to be looking at differences between the treatment and control group, and specifically at time the initial status at time 1. In terms of the random effects, we're going to be computing the variance of the intercepts across students, variance in terms of the slopes across students for time, and because we've asked for an unstructured covariance matrix, we're going to be estimating 3 parameters associated with that matrix: the variance of the intercepts, variance for time, the time slopes, and then also the covariance between the two. So this is essentially at level 2, modeling level 2 outcomes. And then in terms of the level 1 repeated effects, we've incorporated a diagonal covariance structure, and there are 4 parameters being estimated here. Basically, the residual variances at times 1 through 4, and given that there's no covariances assumed between the errors between time points, that's why we only have 4 parameters that are being estimated using this matrix. Okay, so continuing on, when we look at our fixed effects, you'll keep in mind that our control condition for our treatment variable, the control condition was coded 0 and treatment was coded 1. And in terms of the time variable, we had measurement at time 1 was coded 0, time 2 was coded 1, time 3 was coded 2, and time 4 was coded 3. So the 0 reflects the initial status on the math variable, and then the 3 represents essentially the end status on that variable. So when we look at the intercept right here, the intercept is the predicted value on y when your predictors are all equal to 0. So what this translates into is an estimate of the mean for those students who are at the initial time point or the initial measurement, who are also in the control condition. When we look at the treatment variable, this is essentially capturing the difference in means at the initial status between the control and treatment groups. So this is the difference in means. You can see it was not significant at the conventional 0.05 level. And then, which is kind of what you would expect if the students were randomly assigned to the two treatment conditions. Presumably at the initial point, there would be no difference between the groups. With respect to the time predictor, you can see that this is the slope coefficient, which reflects the predicted amount of change or increase on math scores for every 1 unit increase on time. And so we would say that for every increase, 1 unit increase on time, there's a predicted increase on math scores of 31.57 units. And you can see that time was a statistically significant predictor in the model. Now, when we look at the level 1 and level 2 variances and covariances, you can see that the level 1 repeated measurements, you can see at time 0, or essentially the initial status, that there were there was no significant variation in the residuals. However, you do see significant variation in the residuals at the measurements 2 through 4, or on the in terms of the coding on our variable 1 through 3. In terms of the level 2 intercepts and slopes, this is the estimate of the variance in intercepts. You can see that it was statistically significant. So in other words, what this means is that even after controlling for the treatment variable at the initial status, that there was still significant between student variation in their math scores at this measurement occasion. In terms of the slopes, or between student slopes, there's this is the variance estimate, and we have statistically significant variation as well. So in other words, what this means is that potentially we could model level 2 or student level predictors of the variation in the slopes, and that's essentially what the example is all about. And then what we have right here is the covariance between the intercepts and slopes, and so you can see that it's negative, which would basically indicate that students who started out initially with a higher math score exhibited lower levels of change over time. We do see that this is not significant at the conventional 0.05 level. So, given this finding right here with respect to the slopes, then it makes sense to try to model predictors of the slopes, and this is where essentially the authors of the textbook picked up. So we'll go to mixed models and linear, and we'll leave everything as it was, but in this case we're going to click on fixed and click on build nested terms, and then we're going to move these variables down. We'll say time, then click by, and then treatment, and then click on add. And so now we have an interaction term. So in other words, treatment is being treated as a fixed effect, modeling its fixed effect on the randomly varying slopes for time. So now we click on continue and leave everything else exactly as it was. And so now when we look at our model dimension table, you can see we're estimating 11 parameters, and we have essentially the interaction between time and treatment. So this is a cross-level interaction. Like I said, when we look at the students' growth trajectories, we would expect perhaps there to be variation in the intercepts and variation in the slopes. And so we've already sort of addressed kind of the question of variation in intercepts as a function of our treatment variable, and we did find previously that there was still statistically significant variation in those intercepts. So we could also potentially identify other level 2 predictors that might explain that. But now we've also incorporated treatment as a predictor of variation in the slopes between the students, and so that's what we're modeling right here. So when it comes to the random effects, we're leaving everything exactly as they were in our previous analysis. So when we look at our estimates of fixed effects, we have our intercept, which again is basically reflecting our predicted math score at the initial status for those students in the control condition. We look at the effect of time across students, and so this is we see still a significant positive predictive relationship in terms of the relationship between time and math scores. We still, when it comes to looking at the difference between the treatment and control condition at the initial status, you can see it's not statistically significant. But probably most importantly for our analysis is that we find that there is a significant interaction effect. So in other words, this would be, this is kind of what we're assuming in terms of the difference between the treatment and control groups, the increased difference between those two groups as we move from one time point to another. So right here, this is just in Excel. What I've done is I've just gone ahead and created a table reflecting the means for the control group and the treatment group at each of the time points, and then the differences in means that are reflected right here. So this is essentially a plot of the predicted means in the control condition and the treatment groups at each of those time points. And then, like I said, this is the difference. So you can see that that there's a more pronounced slope for reflecting a stronger positive linear relationship between time and math scores, whereas in the control group, which is in blue, there's a weaker relationship. And then this right here is just a plot showing you the difference in means between the two groups over time, and so you can see that. So looking a little bit further then in terms of our covariance parameters, you can see that we still see that there are significant residual variances at level 1 for the second, third, and fourth measurement occasions. And in terms of looking at the variance in the intercepts and slopes for time, you can see the variance for intercepts and slopes. Both of those are still statistically significant, but with respect to the covariance between the two, it's not significant. So there you go. Now, one final demonstration from the chapter. The authors actually started out by kind of discussing a little bit about the possibility that there may be a nonlinear relationship between time and math scores, and so kind of assuming that there might be a curvilinear relationship. So what they did was they actually took the time variable and recoded it into a new variable in order to kind of capture a nonlinear growth trajectory. And the way that they did this, so essentially this is their discussion of alternate coding, and basically time, the first measurement occasion, or the initial status, was coded 0, and the end status was coded 1 in terms of the time variable. And then they basically coded the time, the previous time coding of 1 to a 0.5, and the previous time coding of 2 to a 0.7. The way that that they accomplished this, they just went to transform, recode into different variables, and they just moved the time variable over here, and just as a demonstration, I'll just call this time new. They clicked on change, and evidently I've already generated that, so let me redo this. So we'll move time over. We'll call this time new. Click on change, and old and new values will take the old value on the time variable of 0, leave it as 0 on the new variable. The previous value of 1 we're going to call 0.5 for this new one. Previous value of 2 we're going to recode into 0.7. And then the final value of 3 we're going to recode into a 1. So that gives us the same coding on this variable right here. And so when we click OK, we end up with our this variable right here, which again is the same as this one. So essentially, what they ended up doing, they ran the analysis just by going to analyze mixed models linear, and instead of using the time variable, the original time variable, they used this variable right here. And under fix, we'll just move this variable over, click on build terms, and we'll just move this over here. To model the interaction, just basically we click on build nested terms, and we'll just do the same thing that we did previously with our previous time variable. So we'll click on continue. Under random, we'll move our time variable over as well. And in their demonstration, they don't really specify what type of covariance type at level 2 that they utilized. I tried this previously, and it ended up with the unstructured matrix, and we ended up with problems with estimation. So kind of figured out that what it looks like they did was they utilized the variance components at level 2, so estimating the variance of the intercept and then the variance of the time, our new alternate time variable, but then no covariance between the two. And so when we click on continue, we'll leave all our previous specifications as they were. Click on OK, and so now you'll see that in this case we actually are back down to 10 parameters that were being estimated in the model, because we're using the variance components where we're estimating the variance for the intercept and the alternate coding of our time variable, but not a covariance. So that's why we're down to 10 parameters estimated in this model. When we look at our fixed effects, you can see that we have the intercept, which again would be the control group mean at the initial status. Then we have, the treatment variable would be the difference between the groups at the initial status. And then the alternate coding of our time variable was statistically significant. And then when we look at the interaction, this is this would be the slope for the interaction term, and it was statistically significant. So in large part, we're finding very much similar findings with respect to the interaction between treatment and our time variable. So it was a significant cross-level interaction, pretty much following the same interpretation of what we had before. Really the big payoff in terms of this coding right here was just mainly that if it's not really a tenable possibility that that our repeated measurement exhibited a linear change over time, the idea was to sort of account for possible nonlinear change by recoding our time variable to reflect that nonlinearity. So that's all that we just basically did in this case. But for the most part, many of our interpretations from our earlier run hold in this demonstration. And really quickly, if we look at the intercept variance and the slope variance, we see that both of those were still statistically significant, and we see the repeated measurements in terms of the residuals for each repeated measurements for the second through the fourth time points, we see that those were still statistically significant. Once again, because we did not utilize an unstructured covariance matrix at level 2, that's why we don't have the covariance between the intercepts and slopes for our time variable as we had in our previous demonstration. So that concludes this video demonstration.